Εκτός αν είναι άλλο.
No, I don't see him. Yesterday was with his name. Maybe someone sent him an email. Shall I send him an email? Well, I don't have his email actually.
I mean, he knows the program, no?
He knows the program, Ignatius. Okay, good.
The program didn't change.
Yeah, at all. The only problem is if he happened to us, maybe he mixed the times because these are Greek times. That's what I don't know.
The next speaker is ready. Maybe we can start from the next speaker. So then, are you ready? Yeah. Okay, so let's start then with Christo Harmousis from Orsay, who is going to talk on black holes beyond GR.
Ένα, δύο, τρία. Μ' ακούτε? Yes, can you hear me?
Yes, but we need to share the transparencies. At least I don't see any.
Here we are. I should stand here? Yes, because you get feedback. All right, thank you very much for the organizers to have me here once more. The subject of my talk is a bit like Panayota, it's on black holes. I'm going to talk to you in a synthetic way about recent results we have obtained with my collaborators. This is... How do I have a pointer? Oh, yes. Okay. Okay. So my collaborators here, there's a nice bunch of them. So Tim Anson, who is actually finishing his PhD in a few days, who has been working with Evgeny Babichev. They are my longtime collaborators from Orsay, especially Evgeny, who is Russian, and Tim, who is English and French. There is a bunch of Chileans, Olaf Barke and Miguel San Juan and Mokhtar Hussein, who are in Talca, in Chile. There is Antoine Leibel, who's now in postdoc in Lisbon. Nick Stergioulas, who is an astrophysicist in Thessaloniki. Marco Chrysostomi, who is in CISA, doing a postdoc there. And my also very long-time collaborator and old boss, Ruth Gregory, from used to be in Durham, now she's in King's. Okay. So why are we interested in particular about black holes right now? I think it's a really exciting time for black holes and compact objects because there is a multitude of observational data. You all know about gravitational waves, but also arrays of radio telescopes like the Event Horizon Telescope or the Gravity Interferometer, okay? And of course also X-ray telescopes and other observations that are bringing us, first of all, gravity waves of binaries. These binaries can have been even neutron stars. We have the 2017 that gravitational boundary that came a few years, which was a neutron star merger. Another very interesting 2019 gravitational wave binary, which combined a black hole which is about 20 times the mass of the sun, and another companion, a secondary as we say, which is a 259 solar masses, which is actually what astrophysicists call the mass gap. They believe, we have believed for a long time, that there wouldn't be compact stars, compact objects in between about two sun masses and 5 sun masses. Well, there are. And so this is one of the new things that have appeared. And this raises a lot of questions, because if this is a a neutron star, for example, then it needs a very stiff equation of state, or it needs to be rotating very, very rapidly at a point where it could be, in principle, unstable. And so this raises a lot of questions, which in recent years, in the future years, we'll maybe be able to answer. Now, the Event Horizon Telescope, you know it well. You have this image of, for the first time, of the black hole M87, which is like 4 million times the mass of the sun, an enormous black hole. The gravity interferometer that looks at our Milky Way Sagittarius A star, where we believe that there is, we have very good reason to believe that there's a central black hole there. And not only that, but since 25 years, we're observing stars going around Sagittarius A. And this is like a bit like we observe the planets going around the sun, but now it's stars going around the black hole. So gravity can be even stronger, but it's a lot harder, of course. And we're starting to get the Eddington parameters for the motion of what the star S2, for example, orbiting this massive black hole. Okay, so we will be obtaining orbit characteristics. We have the mass for the moment, but angular momentum and other characteristics. I will come back to that. And in future years, we will be able to see, to test the Loehr theorem and things like that. Okay, and the X-ray telescope, which is observing, basically wants to observe what the equation of state for neutron stars is by looking at time observations of pulsars. Okay, now there are even more exciting things to do. Astrophysicists are very hard looking for pulsars that may be close to the black hole, because then this would be an enormous laboratory for strong gravity, enormous laboratory with time delay experiments. Okay, so this is a very exciting time to look at black holes, and in particular, you want to look at black holes that go beyond GR in order to have some measurable ruler of how you go beyond GR. If you are beyond GR, or if you're not and you're just in GR. Okay, so here we find alternatives to GR black holes as precise rulers of departure from general relativity. Okay, this is our aim in our theoretical research. So in my plan, I want to start just reviewing GR black holes. Okay, then we will move on to scalar tensor. I won't spend too much time on the scalar tensor theory because it's just an effective field theory. I will tell you what I think is important about it and what is not. We will encounter keywords like stealth solutions, and we will use Brandon Carter's work on paired geodesics, for example, to create solutions in scalar tensor theories. So what I'm trying to say here is that what we learned from GR since a number of years is extremely useful even to go beyond GR. Okay, we will use methods which have been used in GR. For example, Gibbons and Pope used them Fairchild method in order to find generalizations of Kerr in higher dimensions very recently. And also we will use deformer transformations, which will permit us, I will explain what these things are, to even create exotic solutions like regular black holes. Okay, tomorrow Thanasis Barkopoulos is going to talk about wormholes even. And also create, solutions which are stationary black holes, which are not the Kerr black hole, which go beyond the Kerr black hole. We will get this analytically. We will have them, the real metrics, okay, not numerically. So this is the aim. This is the idea of what we want to do here. And let me start with GR, okay? So in GR, black holes are characterized by a finite number of charges. They have no hair, as Willett told us, okay? They are relatively simple solutions. They have some mass, some angular momentum, and if you manage to evaluate Q, then you would have to, it would have to be the same as minus G squared over M. Okay. And during collapse, they lose their hair, and they are solutions of Einstein's equation in the vacuum, except if you have electric charge, of course. Okay. The simplest one is the Schwarzschild solution, which you've already seen many times. Okay. This is an asymptotically flat solution. And it has another characteristic, is that at the zeros of R, of f of R, the coordinates are not curvature singularities. They tell you what is the horizon of the black hole, as you see here, okay, which is RH equal to 2n. An event horizon really defines the presence of a black hole in the sense that there is a singularity at the center. It's not regular, okay? The curvature explodes there. General relativity breaks down for sure, okay? But it is covered by an event horizon. So it is really the boundary of the trapped region defining the black hole. Nothing can escape this event horizon, okay? Another interesting aspect that you get from light geodesics is the photon sphere. It is exactly, the photon sphere is exactly what you see in the picture here, okay? Which is about 5 times the Schwarzschild radius. I will discuss this a little bit later on. Obviously, I cannot go too much into details, but what is characteristic of black holes is that they all have a curvature singularity in GR. Now, when we go to rotation, you see the metric gets more complicated, but it's not so complicated at the end. So you have the Kerr black hole, which has an extra charge, where here the parameter is the angular momentum, okay? So this space-time is stationary and actually symmetric. So it has 2 killing vectors, d by dt and d by d phi. Whereas before we had spherical symmetry, it was a static killing vector, which was again dt. Another interesting fact about this solution is that it has the symmetry. It is a circular spacetime, which means that if I change time and the angle phi, I get the same metric. What this means intuitively is that if I am observing this black hole, which is rotating anti-clockwise, it means that in the past it was rotating anti-clockwise. Okay? Actually, all vacuum solutions in GR are circular. But this is something that will change in scalar tensor theory. That's why I'm mentioning it. Now, there's another amazing fact about Kerr, is that its geodesics are integrable. This is true for Schwarzschild, because you have, in order for it to be integrable in 4 dimensions, you need 4 constants of motion. That means that you can write a geodesic equation as a first-order equation. And indeed, here you have, for each killing vector, here you have rest energy. You have a charge associated to it. You have angular momentum associated to d phi, which is going to be conserved. You have the mass of the particle, the test particle, which appears here. But the amazing thing is that there is also a killing tensor that comes along, and the Hamilton-Jacobi potential, which is S here, ends up being separable in R and theta, as was proven by Carter. Okay? And then geodesics are integrable. So basically, we can know what's happening for geodesics around Kerr spacetime, which is important for the photon sphere, for the black hole shadow, etc. I will read this later on again. So this is the picture that you have of Kerr black hole. This is I stole from Matt Visser from a very nice paper in 2007. So in Kerr you have static, which are defined by this killing vector, and you have a combination of the 2 killing vectors to define stationary observers. As you come out from infinity, GTT or d by dt, the norm of this killing vector, becomes space-like inside here, and this defines the ergosphere. Okay, the ergosphere is a region in blue here, which when you can get out of it with even more energy than you came in. Maybe you've heard about black hole bombs and things like that. It's a very interesting region, which is in Kerr. Okay, now in this here, no static observers exist. So you have to flow along with a black hole. You have stationary observers, which are here, and stationary observers cease to exist exactly in the red curve, which is the horizon of the black hole. Okay. So as I was mentioning, you have time-like and null geodesics. They dictate the trajectories of test particles in the vicinity of the black hole, and very important. Also, Brandon Carter showed that Kerr is a causal spacetime, as long as it is a black hole. So as long, because if you have n greater than a, you have a naked singularity, and then you also lose, you have closed time-like curves, okay, which don't exist in the outer region of Kerr. They exist in the interior, but that's not a problem. Just like the ring singularity, because the thing is rotating, the point singularity has become a ring. So, when I go on to scalar tensor theories, the interesting thing about them is that they are the simplest modified gravity theory with a single scalar degree of freedom. It's as simple as we can get, all right? And the other interesting thing is that scalar tensor theories, and I think that it's not that there's some fundamental theory, but they are a limit of most modified gravity theories. So if I think about, and I also talked about the Randall-Sandra model or the DGP brainworld model, they, at some limit, you can have a single scalar there. Or Ignatius talked to us about effective field theories in string theory, where you also have a multitude of scalars, okay? So, or even if you take by gravity or massive gravity, there is a limit where you have a scalar tensor theory. Even if you start changing and you start inputting torsion or non-metricity, you can see it sometimes, one of the extra degrees of freedom comes out on top, which is a scalar degree of freedom. So in what I want to say by that, there's nothing fundamental about scalar tensor theories, but it's nice because in scalar tensor theories, we know in 4 dimensions what is the most general one, okay? And it is what they called DOS theory. We started with branch decay or Kordensky, beyond, and then DOS theory, which is parameterized by 6 functions of the scalar field and the kinetic energy of the scalar field, which is given here. And I just want to picture this. You see, you have higher order operators, okay? And the point is that you want to look at these theories because branch decay theory, due to no-hair theorems, only have the GR black hole solutions because there the scalar has to be trivial. Otherwise, the solutions are singular, okay? So what about these relations in these DOS theories between them? So Kordensky, beyond Kordensky, DOS. So here I'm giving you an example of a Kordensky theory, okay? It's one of the simple examples where my functions have just become, you know, just constants here. Now, the point is that if I take conformal and disformal maps in DOS theories, well, I stay in DOS theory. And the second important part is that if I start with Kordensky and I do disformal and conformal, I go to DOS. So my point here is, what the message I want you to keep is that maybe if I have one black hole solution and I do a disformal transformation, I can create a new black hole solution because I will stay in DOS theory in the sense that I will be still in a well-defined scalar tensor theory. So I will use this. This is a picture that David Langlois wrote some years ago. So we want to construct black hole solutions and we start with spherically symmetric ones. So I take this theory we took with Evgeny Babchev in 2013. The amazing thing is that you can find a general spherically symmetric solution as a solution to some algebraic equations. And the simplest of solutions reads like this, with a scalar field which is really not trivial. And this is a stealth black hole because, now what do I mean by stealth is that what you see here in the metric is just the Sitter-Schwarzschild. The only difference is that the de Sitter part, okay, is not the lambda that you see in the action. They are related via this Q integration constant, so it's like a self-tuning solution. Anyway, the interesting thing that was noticed later by some Japanese colleagues was that for this solution, X is actually a constant, okay? So, as I was telling you before, I can do a disformal transformation of this solution. I will still stay in DOS theory when I do that. I will go to a new theory. But the funny thing is that although you can do a coordinate transformation of this resulting solution, okay, and you see that it's still a black hole, it's still like a stealth solution with different charges, with a different cosmological constant and a rescaled mass. So the disform metric has given us again a new black hole, but again a stealth black hole, which has the same metric as the GR solution. So for spherical symmetry, we can find this generically in DOS theories, as it was found later. But now the real difficulty is how to implement rotation. You see, disformal transformations didn't give us anything really new. So can we construct, as a first question, stealth rotating solution? So metric care with a non-trivial scalar field, okay? So For spherical symmetry, we have a GR metric and X which is constant. Can we obtain the same for the Kerr metric? Well, we tried for the theory I was showing you before, and it didn't work. But a certain time, we managed to go forward, but because the idea was, the main thing that was questionable, what is the scalar field? You just cannot take any scalar field, or already it's very complicated. And then what is the theory permitting such a solution? And basically the idea came from Ruth Gregory when we were discussing together, who told me, well, if your X is constant, basically if you take a derivative of it, it's just a geodesic. Or, in another way to say it, my scalar field, remember this is just the kinetic term for the scalar field, can be the Hamilton-Jacobi potential. And for Kerr, we know what the Hamilton-Jacobi potential is because Brandon Carter found it for us years ago. Okay? And it turns out that for certain DOS theories, the ones which are very close to GR, they're the ones that where gravity travels with the speed of light. Okay? Exactly these. You can get a self-Kerr solution with the scalar field being the Hamilton-Jacobi potential, which you can manage. This is the Hamilton-Jacobi potential, and as I was telling you, it's separable. And of course, now you have to think a little bit because geodesics will depend on these parameters. These are the trajectory parameters of a test particle that you throw out from infinity. Well, you know that geodesics don't necessarily visit the whole of space-time. Okay? In particular, if they have angular momentum, they don't visit close to the north or the south pole. They cannot visit there. So it is not trivial, but you can find a bunch of characteristics so that the scalar field is regular everywhere. So from the beginning of the event horizon up to asymptotic infinity. So this is now a well-defined solution for the Kerr metric with the scalar field in this particular DOS theory. Okay, so now what I'm going to do is I'm going to do this formal transformation of this solution. Okay, and what do you get? Well, so I do this formal transformation, which is not so difficult because X is constant. So D of X is just some constant. D is some like deformation parameter. And indeed, it is a deformation. It is a real deformation of Kerr. This metric that you see here can never be Kerr except if D is equal to 0. And why? Because it's very easy to check that for D different from 0, this is not an Einstein metric. So it cannot be a GR solution. So now you have this stationary metric, we don't know if it's a black hole, okay, which has been created by this formal transformation of the geodesics that we have used, which are regular everywhere, which is a solution of DOS theory and is a real different solution from Kerr. So this is, now is it a rotating black hole? So for each D, we have a new stationary solution. So you can think of it, this parameter D, you have to be careful because for each D, I go to a different theory. It's a theory parameter. But I can think of it phenomenologically as D being a disformability parameter, taking me to a different black hole, which is other than Kerr. Okay? So in the absence of rotation, I explained to you before, like for Schwarzschild, it's just a coordinate transformation. But when the metric is rotating, the metric is not an Einstein metric. Now, the metric that I showed you before has a ring singularity like Kerr. It has an ergo region like Kerr. It is a causal spacetime, okay, which you can prove using a theorem in Wald's book. And it has an event horizon, so it is really a black hole. However, it's not so simple because the horizon in this disformed Kerr metric is not a constant R, it's a R equal to R theta surface. And as a result, the event horizon is not the killing horizon in this case, because you don't have the GR usual theorems anymore. And stationary observers cease to exist before hitting the event horizon. Okay? So there is a region, there's a little sandwich, where your stationary observers will be space-like, but there will be directions in R and theta where you will still be able to be time-like. Last part, space-time is not circular. okay? And this is because this dTdr term here, which you cannot gauge away. The physics are not integrable. But asymptotically, we have something which is very close to Kerr. You have higher order corrections, of course, and you can go and calculate the PN parameters we did in the last paper. And we see, for example, that for whenever D is different from 0, you don't have the no-hair theorem that I was telling you about. So if you could measure Q, J, and M independently, and the no-hair theorem equation was not valid, then you would be in such a case. The last thing I want to tell you is we can use solution generating methods in order to construct regular solutions. Now, in GR, I told you that the center there is a singularity, right? But here you can, using the Kerr-Child construction, you can construct solutions in DOS theory, which are regular black holes everywhere. So that means that this metric, as you see it here, look at it. As you go far away, this looks like Schwarzschild because arctan will go away. But as you go in the core, okay, the metric is regular because the metric goes like 1 plus something r squared. It has a de Sitter core, as we say. X of r here is not constant, okay? And if you look at the horizons, you always have an event horizon for a certain mass, but you also have an inner horizon, like horizon nostrum. This is typical for regular black holes. And it becomes extremal at some point. When the mass is not big enough, there's no horizon anymore. And then this is like a soliton. This is a really regular particle-like solution made out of gravity. And in particular, we can look at light geodesics, and you can write the light geodesic equation as a Schrödinger equation with some effective potential. This is like you would do in quantum mechanics. And there you see, indeed, the red curve, this is Schwarzschild. And the maximum here, where V prime is equal to 0, is what I was telling you is the photon ring, is where photons, it's the closest photons can go in without being eaten up by the black hole. Okay? And here, indeed, you have something similar. Here you have the regular case, and your photon ring is shifted a little bit in the interior. But once you stop having an event horizon, you see your potential goes out here. And so instead of the picture where you had the light ring and the nothingness black in the center, here you would have some light, some stronger light, and this would be an effect of like a particle-like solution in gravity. Okay, and now I'm finished. So this is, we have seen how to construct non-trivial scalar tensor black holes, which are well behaved, okay? We used classical results from GR and mathematical symmetries in order to construct many phenomenologically interesting solutions that can be used like D. You see, if D is different from 0, it's really like a ruler. Can I go away from Kerr, and how much can I go away from Kerr? Okay? We can even construct exotic solutions like regular black holes coming really from an action where the mass of the black hole has nothing to do with the coupling constants of the action. Okay? And Thanasis Bakopoulos tomorrow will talk to you about a wormhole construction in these theories. Okay? So, for the moment, gravitational waves, the Einstein Horizon Telescope, give certain constraints, like for instance for the light ring, for the coupling parameters. They basically tell us more about the mass than anything else, but there's a lot more to come in the future, and then we may or not see key differences with GR. And that's all. Thank you.
Thank you very much. Are there questions from the audience? Yes.
I mean, I don't work with these formal theories, but when you do this formal transformation, just to make it clear to me, usually you are getting high derivative terms in your action.
Yes, you can. Actually, this is a good point, Apostole. In fact, you can see. No. Actually, this is the point. Can I have control of the slides, please? No, this is a very good point, and I didn't say it. I should have. The point is that, you see, when I'm in Kordensky, I didn't go into that. Kordensky showed what is the most general scalar tensor theory that has second-order equations of motion. Okay? A bit like Gauss-Bonnet higher dimensions. All right. For a long time, we thought that if you added higher derivatives, you would get ghosts. Now, then it was shown that you had these beyond Kordensky theories that didn't have a ghost. So you do a Hamiltonian formalism around an arbitrary spacetime, and you see that you have still 3 degrees of freedom, 2 for the metric and 1 for the scalar. And this is also true for dust. And then people realized that, in fact, these extra 2 functions that you have in dust theory are nothing but the conformal and the disformal transformation you can do in Kordensky. What this means is that when you do conformal and disformal of Kordensky, you don't create a new degree of freedom. You still create a healthy theory, okay, which has 3 degrees of freedom. And this is. Yes, you can. In fact, in that case, you have that. I cannot talk to you, seeing you. In fact, what you have in this case is that there are no.
I think it was me.
There are no higher time derivatives.
No,
You have special derivatives, but not higher time derivatives. That's why it's regular and fine.
Any other question? Yes, Fabian.
Thank you. Christo, you said that when you consider the solutions with chi being a constant,
X, yes. X.
being a constant in the case of Kerr black holes, then you can actually match that to the Hamilton-Jacobi potential.
Exactly.
Does this apply also for other type of backgrounds, not for the Kerr?
Oh, yes, absolutely,
So
absolutely.
It's
It's a general observation that many of these solutions, especially these, you see, you may have asked, why do you take this time dependence for the scalar? This is precisely because a geodesic is allowed to have this, because I have d by dt a killing vector. We didn't realize it in the beginning. But as long as your theory is only depending on x, not on phi, and then it's shift symmetric, you might have x constant solutions, and this x constant means that they come from geodesics of the space-time metric that you have in question there. It might be Kerr, it might be some exotic space-time, it might be what you want. But x constant means it's a Hamilton-Jacobi potential. Yes.
And something very fast, in the case of the regular black holes,
Yes.
so massive particles can actually cross the horizon area and get out of the other side, or they are trapped?
But they will come out in a different universe, I think, because I don't think it can be topologically related.
The scalar fields are regular in the regular solution?
Yes.
And the metric?
Yes.
I mean, their metric.
In the regular black hole, X is completely regular, as you saw it. For the scalar field solutions for stealth, you have QT and something that explodes at the event horizon from R, but because T also goes to infinity, the singularity goes away, and it's completely regular. You need to have the time dependence in order for them to be regular. Yeah.
Maybe one more short question from the well, one of them. I don't know which one of them. Choose one. Okay, Nick.
Okay, nice talk, Christos. My question is quick. Your wormholes are stable in the sense that you have exotic matter, or you are facing the same problem as usual?
Thanasis will talk about this tomorrow.
Okay.
They don't need exotic matter. Yeah, I can certainly answer you this. If they are stable to small perturbations or non-perturbative perturbations, I do not know.
Okay.
Thanasis will talk about this tomorrow.
Thank you.
Okay, I think we can stop here because already the time is over. Thank you very much.
Thank you.
All the answer is online, but I would propose not to switch between to postpone one more and have one more if you agree, and if Jean-Frère is ready. Hello, Jean-Frère. Are you ready to speak now? Because it's better, I think, not to switch between online participants. If you are ready, then you can.
I was just thinking what was the moment to concentrate before the talk. Half an hour. Put this on, and I try to find a space where I don't have Larsen. I'm exploring a bit. Okay, seems to be working. Good. I assume this works as usual. Okay. So this is a very, very simple talk. It's more a reflection of thoughts, and of course, I will not answer the question. I don't have an answer. There is maybe one thing for us humans is we are trained to look for patterns. For example, as soon as some panorama of the planet Mars comes around, people start seeing human faces in it. So we have some kind of automatic search for some patterns, which of course leads to some bias. And we may wonder whether the searching for symmetry is sometimes such a bias. We may be looking for symmetries where they don't exist. Of course, here, if you see a catamaran boat, you try to align with it, and you align with the sun, and the result starts looking symmetrical, of course, because you walked just enough to get it symmetrical. Well, this is a joke. I'm trying to use some pictures from here to make it more okay. So the thing is that when we know the answer from the standard model, parity violation is the default expectation. When you start with the standard model, it's completely a chiral model, and we should not expect to have parity restoration. Still, over the centuries, we have lived with the idea that the world was symmetric between left and right. Not that it is symmetric between left and right, but that it should be symmetrical between left and right. We have seen left-handed and right-handed people, but you thought, okay, well, this is a bit quirky, but that's life. There is a majority of right-handed people. Strange, okay? All those people have left-handed DNA, but okay, so what? Probably the first DNA was left-handed. So basically, we have moved to, which we always do in physics, to the idea that the rules themselves are symmetrical, and that the boundary conditions are violating them. And since we are not supposed to predict the boundary conditions, then life is good. So it's reassuring. And in fact, when we looked beyond, I would say, human beings, well, living beings and so on, we saw that in all practical experiments you can do on Earth, basically left and right are equivalent. I don't mention the Earth rotation effects in this. I mean, okay. When we do an experiment, we look at it in the mirror, and the experiment we see in the mirror is realizable. We have no way to tell it's not a physics experiment. The same is true to a large extent for time reversal. If we film a mechanics process, of course, it's reversible as long as we don't get entropy in it, aging, or heat dissipation. Good. Then Yeah, okay, you know, well, of course, this is true for electromagnetism because, of course, you use a right-hand rule in electromagnetism and you use it twice, so it doesn't matter if you take a left-handed or right-handed rule. Okay, now parity is broken, and it's interesting. I hate history, but it's amusing to see how it was discovered. The first evidence for parity breaking was the theta tau puzzle. People discovered two particles of masses about half the mass of the proton, one decaying into 2 pi, one decaying to 3 pi. By that time, it was known that the parity of the pion was negative, and therefore this seemed to be a contradiction unless you accepted parity doubling, which was a very seriously considered solution, or you accepted parity violation. Now, those guys, I put this tau with a capital tau because to avoid confusion with the lepton. Okay, so in fact, the first discovery of parity violation was in the hadronic sector. Nothing to do with neutrinos. I will come back to that. Okay. But it was so challenging to accept the parity breaking solution that people wanted a clear demonstration, something they could explain on TV, for example. Well, TV was certainly already in the States, maybe not yet in Europe, but that led to the Wu experiment, which we all know, where electrons are emitted backwards with respect to the spin of the cobalt. And this is a pseudoscalar, this is a pseudo vector, this is a vector, the scalar product is a pseudoscalar, and this pseudoscalar is found to have non-vanishing average value, which is certainly a parity violation. This is many ways to say the same thing. But at that time, the idea came that, well, it's parity violation, yes, but it's parity violation not in the forces. You have a vector there. By the time we knew it was V or A interaction, and you have a vector there, you have a vector there. But imagine simply that the right-handed neutrino does not exist. Okay, we had no reason to assume the right-handed neutrino existed or did not exist, and you work out the spins here, you know, the spin of the nickel, and you solve the thing by keeping only this diagram. Notice that here I've put the vector particle in blue, because that was the understanding. You have some kind of vector boson couplings to neutrinos and electrons, and tough luck, the neutrino right is not there or is too heavy, and therefore we have parity breaking. So once again, the parity breaking in this approach for a long time was not via the interactions, but in a way via the boundary conditions. Somebody had forgotten to order the new right, or the new right had been gaining too much weight. And therefore, we started at that moment with a folklore that parity violation was linked to the absence of the right-handed neutrino. And we ended up with many courses about weak interactions, starting with the absence of the right-handed neutrino to build the SU2 left cross U1. And going to affirm that, okay, the neutrino right is excluded by Weinberg's paper, Glashow-Weinberg-Salam. Well, nothing excludes the neutrino right in those papers. Simply since there was no evidence for a mass of neutrino, the Dirac term with the mass of neutrino was not written. Was actually, you know, lots of things were not in that paper. The charm part, for example, was not in that paper. Okay. In fact, this is not true, because we know that parity violation is not linked to the leptonic decays. It was first found in k to 2 pi and k to 3 pi. These are the theta and the tau. And therefore, you got this difference. Again, people wanted to check, and the second the second proof of parity violation in the standard model was the discovery of parity violation in atomic decays. And at that time, it was seen that the electron left and the electron right had different couplings to the Z, which means the different interference term. And therefore, we had parity violation once again without any single neutrino inside. So that's really how you get to the idea that indeed the parity violation is involved with the gauge group with the, the parity violation is involved with the gauge group, is SU2 left cross U1, and SU2 left couples only to the left fermions. Well, at least we had it for the first generation. After that, it took quite a while for the people to get used to the second and third generation, because each time we had to measure the coupling of the quarks, and that was, I don't know, 15 years of work. Each single quark chiral couplings has to be checked. So at long distances, parity seems restored. We have already said it. And it looks like nature has been doing everything to fool us into thinking that parity was respected, and that it took strange machines like Wu's experiment to prove the contrary. Actually, yes. And why? Why is it so? If we take SU5, well, all the fermions, you can put them all in left-handed multiplets. Certainly the 5 has only one chirality. Okay, so it is broken. But we still emerge with a vector-like coupling to the photon and a vector-like coupling to the gluons. I would consider the gluon interaction to be long distance. It's long distance with respect to the W and Z. One possibility to explain that, I'm trying to find reasons, is that in the models that we are using, we need to have anomaly cancellation. And that's certainly one criterion. And since we have been living with relatively low representations of the groups, we cannot build we cannot couple the photon or the SU3 in a way which is not parity invariant. For SU3, for example, we find 3 and 3 bars, and we never find the 6 in the lowest lying in the representations of SU5 which are used. So I didn't do, certainly I didn't do comprehensive studies of anomalies in those cases, because the whole point is in the usual representations, you end up with only 3 and 3 bars as like particles, and therefore SU3 would be parity respecting. Now, of course, there is one answer, is that the reason why we have parity conservation in long distance forces is that long distance forces are gauge invariant, remain gauge invariant. That's why they are long distance, because the photon is massless, and let's say that the gluon is massless. And as soon as I have a mass term here, this mass term may result from some broad angular Higgs breaking, or it can be a genuine mass term. This, at this stage, behaves as a number. If I do a phase transformation, a gauge transformation, alpha left phi, alpha right phi, but you see there is only one solution, that alpha left has to be equal to alpha right, which in practice means that the gauge charges of the left and right-handed fermions have to be equal. So at this point, the question becomes that basically, let me just go back, basically the reason we would have that parity is restored at long distances, this is true for for the U1 electromagnetic, this is true for SU3, the reason would be that we only have massive fermions to be charged. The neutrinos are not responding to directly, not directly coupled to the photon or to the gluon. And as long as we have only massive particles to be charged, which is a very old hypothesis that all charged particles had to be massive, then we would have long distance parity conservation. Well, this is not an answer from fundamental laws. This is an answer from the fact that the zoology, I have more than enough. The point is that the zoology of the particles we have does not include any charged massless particle, okay, for some reason. So once again, don't blame the fundamental forces, blame the zoology, the boundary conditions. Well, we may wonder, we want to go further, if it would be possible to have massless, I have to beware of that speaker in my back, whether we could have massless particles which are charged. For example, you can think of a light, very light electron, left-handed, emitting a photon, which is polarized, fully polarized left or right. And of course, this would lead to a right-handed electron. And if you do that forward, you indeed get a linear divergence in this, which means that the massless limit is really a problem. And it's a problem because, in a way, as soon as you have a small mass, you have an E right. But if you have a zero mass, you don't need to have an E right. So it's a bit funny thing. Actually, this was looked a lot at, not a lot, but it was looked at the start of HERA because there was a fear that this would be a background for right-handed currents. And actually, the limits can be reconciled. There was a controversy. I tried to download some of the papers. I only downloaded one. There was a controversy for a while, but the idea is that, let me just, sorry, okay. The idea, if you want to solve that limit, is that you are not allowed to speak of a beam of left-handed electrons if they are massless. It will always be degenerate with a right-handed electron with a photon parallel to it, a soft photon. So in a way, you have to do something like the PDF treatment that is used in QCD for those collinear anomalies. So, okay, it seems to be just a feat of nature that it has chosen not to have massless particles, and that leaves us with the interrogation of why parity is conserved. But actually, I've been lying to you. Parity has not been seen, parity variation has not been seen at short distances, but even in the framework we have with massive fermions, where it should be restored, we can still have parity violation at long distances. Well, in fact, we can build magnetic moments. And we know that magnetic moments are both parity and time reversal breaking. They are charge conjugation conserving through CPT. So they are P and T breaking things. Well, we have not seen one yet. We have limits on the neutron electric dipole moment, the electron electric dipole moments, and even the proton electric dipole moments. Now, it's interesting to have both the proton and the neutron electric dipole moment limits, because if you make the difference, you may isolate the theta component in it, which would be common. And as long as you only measure the neutron dipole moment, you don't know what comes from theta and what comes from loops in the standard model or left-right models, right? Okay, okay, it's parity breaking because it's because essentially, except in non-commutative theories, which is a strange story, but in general, the only direction on which the electric dipole moment can be aligned is the spin. This is a fundamental particle, only as a spin. And then it's the product of the electric, I should say dE, on the spin, which is a pseudoscalar, which is, of course, violating P and T because the spin flips under T. Under T, yes, right. So what does that mean? Well, imagine we come up with some electric dipole moment for the neutron. Something like the 10 to the minus 25 Bohr magnetron, which is the limit for the moment. And we do a double Stern-Gerlach experiment. The Stern-Gerlach experiment is this one, where you put magnetic coils here. They are of a funny shape so that your field is inhomogeneous, and that means that the particle will move in the field. If you put a homogeneous field, nothing happens. And here you do exactly the same, but with a condenser. Minus and plus, this is just an electric condenser. And you look here, you shoot a particle, you have the spin, the magnetic moment, and this is a trajectory of the particle. And then you do the parity operation. Now, I've been nasty, or rather, I've been lazy, because I took some old graph I had done for time reversal. So I didn't give you the parity reversal here. I gave you the time reversal. If you do time reversal, you observe that the trajectory would be this one. That means that somebody taking a movie and showing it to you backwards would be exposed for his fraud, and you could tell, no, sorry, you are cheating. Somewhere there is a neutron moving in your field, and it doesn't move like it should. Yes, this is an example of time non-reversal, and for me it's an example which is interesting because it shows clearly that what happens is that the backwards and the forward itinerary are different, but there is no difference in entropy between the two. It means I take one path to go to work in the morning and a different one to go back home in the afternoon. Okay, now if you want to do that with P, I suggest you make a reflection on this plane. Now it's always, parity is always easy at the point, at the point interaction level, but it's tricky when you have an apparatus. You can put a mirror here, you can put a mirror there, you can put a mirror in front. I think if you put a mirror here, you'll get pretty much the same thing. So it might be, in fact, that there is no paradox that parity is not respected at large distances. Well, this is 1 over r cubed. This is not 1 over r squared forces, but okay, 1 over r cubed I can live with. And that, in fact, we could maybe not have been fooled had the electric dipole moment been a bit larger, in which case we would be in the case where we are looking for symmetries where they don't exist. Oh, well, this is my lunch, by the way.
Very much. Other questions from the audience?
I should say that when I put the calculation.
Excuse, yeah? Can I ask a question?
Yeah, after my question, you can ask a question, Holger. Right, so the polarization, so the fact that we have a different theory and different predictions with a massless particle, for example, a big quark, okay, in the polarization, or a situation where you take the massless limit of the theory, you get to predictions, and this is due to anomalies. This is seen in some calculation, which I seem to have done that more than 20 years ago. In E plus E minus to bottom BB bar using lambda baryons and so on. And you get a difference which is, as far as I could see, of 3%. And with the precision you can see, you get, you can check in principle your assertion that you can, that the theory behaves differently. And this is because of the anomaly. So it's a different theory where we have a big quark or a quark or whatever, or fermion, which is massless. You take the mass limit, but the field is there, and a different prediction when the field does not exist.
Yeah, I think usually, at least this is, you know, the thing I mentioned is a paper of Einhorn and Kontopanagos a long time ago that I remembered while preparing this talk. And there was quite a bit of controversy at that time. And people didn't think immediately of applying the same treatment as is done in deep inertistic scattering or whatever, and putting the degeneracy of the states in the incoming beam, which means that when you have a massless fermion, it's always degenerate with the massless fermion with the photon. And that's a question of taking the limit. Now, I've not... Yeah. Yeah, but here in practice, if you integrate over the soft photons in the beginning, if you do an operational description of the experiment, you get no paradox in this. And the worry was that there would be a diverging right-handed current seen the moment they switched on Hera. Sorry. I think there was a question from Nick. First of all, is there any other question here? No. Okay, so you can ask.
Yes, I would like to say, you talked about this empirical rule that charged particles were massive. But I think in this connection, one should probably think about and mention also that there are requirements in gauge series for anomalies canceling each other. Otherwise, you can't keep the gauge symmetry. And it is rather tricky in the standard model how these cancellations are fantastically smartly canceling each other. But if you only had the low energy, the long distance, as you say, forces for QCD, and to get the anomalies cancelled, in that case, you might get only a trivial cancellation, but the trivial cancellation.
Yeah,
means that you have equally many rights. In that case, charge as if the particles were massive and had a definite charge.
Cancel or don't cancel, they do cancel. This was just a hypothetical where the mass of a lepton goes to 0, in which case we need to do some soft photon resummation. And so there is no big worry in it. On the other hand, it does not clear the answer why we have been fooled for so long by nature that it seemed to be symmetrical. That's. I see there are other questions. But maybe we have to.
You can ask.
Yeah, in the Zoom we have some questions. So.
May I ask you, Alexander Studenikin speaking?
Nico.
Oh, yes.
So sorry, I'm first. What in your assumption on the? Thank you very much for your nice talk. In your assumption for p violation, you assume CPT conservation. Suppose that CPT is violated for some weird reasons, quantum gravity, or whatever. What would you have to say in that case, hypothetically, for p violation at long distances through dipole moments?
I think the argument for p violation at long distances remains the same, whether CPT is there or not. I only use CPT to say that charge conjugation was conserved. But since we are not going to do EDM experiments with antiprotons, it's not going to affect the experimentalists.
Thank you.
Thanks for the question.
Last question from Alexander.
Yeah, thank you. Thank you for a very interesting presentation. So you have mentioned that in our day life, we always observe a kind of symmetry between left and right in nature. Well, does the direction of shells twisting present a counterexample?
Sorry, the example of
symmetry that we observe in between left and right that we observe in our day life in nature.
Yeah, but which was the example? I didn't hear it, sorry.
The twisting of shells, it always in one direction. I don't remember in left and right, but it always in one direction.
We have lots of things on Earth with sometimes people link it to the Coriolis effect, but simply all DNA is wound in the same direction, is left-handed. I don't know how they define left-handed there, and we only process efficiently left-handed sugars. There is lots of examples, but that's all what people have always put in boundary conditions. I say, well, all DNA is left-handed because the mother of all DNA was left-handed, and we have kept it that way. That's boundary conditions. That's what I'm saying. We are trying to always find an excuse for the real theory to be more symmetrical than what we see.
Okay, well, thank you very much. Thank you very much. Thank you.
Stop here. Let's thank the speakers. So the next speaker is Fabian Nielsen, remotely. Holger, can you hear? Can you hear me? Just maybe you unmute him. Can you unmute yourself? Can you turn on your microphone? Holger, can you turn on your microphone? Okay.
Yes. Thanks. I am.
Holger, can you?
Thanks for. Yeah, I'm trying to share screen. Thanks for atomic size.
Give him rights. He has no right, I think. Oh.
Do you see any screens?
Please, those who would like to come tonight in the Greek dinner to sign.
Can you see my screen now?
Yes, Holger, we can. You have to make it a bit larger, please. Yeah, that's fine. Now it's okay. Very good. Great.
5 minutes, Holger. Please, go ahead.
Can you hear me?
Yes.
Now I can't hear you. Hello? I'm not sure you can hear me or not, but I would
in the Zoom we can hear you.
Thank for being allowed to the co-organizers. Can you also see my screens, my slides?
Yes.
Yes.
You can? Okay. So I would like to thank organizers for being allowed to give this talk about our model of dark matter, which is a model in which the dark matter are small, almost macroscopic pearls of the size a little bit smaller than atoms. And it's called also electron. And then I'm using this notation that dark matter should be WIMPs, which means weakly interacting. But in our model, we don't have them weakly interacting. In the shield in the earth about the laboratories in Gran Sasso, and they should rather be self-interacting dark matter. You can see these shorthand writings: IMP, interacting massive particles, and self-interacting dark matter, CDM. And let me stress that this is probably the most important point in our model, that the dark matter is stuck in the shielding, and it emits energy as electrons or photons perhaps, but not by having excited nucleons, because it gets stuck so early in the shielding that it comes down to the laboratories very slowly, centimeters or meters per second. So, or thermally, basically. And therefore, they are not seen by the usual experiments with xenon, but the Dana experiments see them because they emit some energy because of being excited. So the main point is that they get stuck in the shielding because they have high
Please, can you unmute yourself? There was a problem here with the connection. Unmute yourself in the microphone. Holger, can you turn on your microphone, please? Doesn't understand. Doesn't hear. Hello, can you hear me? Holger?
Yeah, we cannot hear the speaker. At least I cannot.
Can you please unmute yourself?
Holger, you muted. Can you unmute, please, as Ignatius says, if you hear me?
Holger? He doesn't see it, I think.
Am I now unmuted?
Yes.
Okay. So now I will find my slides again. Where happened to them? You share. Yeah. Now I am trying to allow you to see this again.
Yes, it's okay. It's okay now. Let's continue.
So now what it is that the particles get stopped and they emit electrons or photons, so that they are, that they are not seen if the experiment looks for recoil nuclei. And now let me tell our model, but it is probably not so important as this that it stops and that it can get excited. But here we have a concrete model which is consisting, the particle is a little pearl, so to speak, and the pearl has a radius of some 10 to the minus 11 meter, which means something a little very small atom, especially for so high charge, because the charge is supposed to be of the order of 100,000. And there are 100,000 protons or neutrons in it. And then these are put into a new type of vacuum. And that's the really speculative part of the story, that there is a new type of vacuum. And on this figure, this is the region inside the radius capital R, or essentially the same, called R cloud 3,3 MeV. And this is about a few times 10 to the minus 12 meter. Here are the numbers of this. And this is sort of fitted numbers, but I want to stress that this fitting is somehow rather successful. So here is another representation of the pearl, where we see going to the left the radius out from the center of this, in reality, atomic light particle, and this atomic light particle has a potential for electrons, and it has a lot of electrons in it, of the order of 100,000. And the electron potential is the line which goes up to 0 and then somehow negative, and then flattens off at the bottom very close to the radius going to 0. And then there is these two radius parameters, where the potential takes the values which are written as index to the little r. I hope you can see that the electrons are extending only to the distance r with index 3,55 keV. Actually, I will ask you to keep attention to this number 3,55 keV, because that is the frequency or the energy per photon of an astronomically and by satellites observed mysterious line, which is supposed to come from dark matter. And that's also what we hope. So, but here it is that the electrons, because of a Homolumo Gap Effect, which I will talk a little bit about in a second, only come out to the distance where the potential is down by 3,55 keV. And then in between this distance where it is 3,55 keV, the potential, it is like an ordinary atom with a lot of electrons, a very high set atom, which the potential goes down and reaches 3,3 MeV, which come from some numbers we have fitted. And then it flattens off, because downstairs is this region where we have this new vacuum I talked about. And then I owe to tell you this Homolumo Gap Effect. And this is, I think I will simply just try to tell very shortly. For a system like a molecule, then Jan and Taylor were the initiators of this idea of Homolumo gap. But the idea is that when you have some, this drawing here is is telling the spectrum for a single electron in some complicated particle like our pearl or like a molecule or so. And then it is so that in first approximation, the Fermi level, the small black balls represent the field levels, and the lines without dot means the empty level. And then a priori, there will just be a Fermi level depending on how many electrons there are. But now, if the system has some degrees of freedom that can yield and give in to forces, then it will tend to lower the field levels and not the empty levels. So in this way, there will appear a gap between the highest occupied molecular orbit, as chemists call it, HOMO, and a lowest unoccupied one, which is called LUMO. And this is the Homolumo gap, and that plays a very important role in our model. And this is taking in our model the value which I asked you to remember, because it was this frequency of the radiation, X-ray radiation seen from the universe, and not ordinary atoms or ions would give it. And then this is the 3,55 keV in our model. But it's a very general effect, and we hope that it works. And I have explained why it is called so. And the name is from this highest occupied molecular orbit. Molecular orbit is, of course, just single particle electron state. And yeah, some troubles to hear me? Or and we believe that we can estimate this Homolumo gap by essentially dimensional arguments or by using Thomas Fermi approximation. Actually, our calculations are very crude, but they are based to a large extent by this Thomas Fermi approximation. But it is, at least we have the formula here, number 2, for the Homolumo gap, which is called here EH. And if we now want this Homolumo gap, according to this formula, to be 3,55 keV, the line of the radiation X-ray from the, supposedly from the dark matter, then we need the Fermi momentum, which is here called PF, to be 3,3 MeV. And that's why we are interested in this potential being 3,3 MeV, because that is where you can have inside the atom this thing, and that is where we are in the pearl, in the middle of the thing. Here is put just numbers on, but it's the same drawing as before. And you can notice these numbers, that they are 3 times 2 times 10 to the minus 11 meter, a little bit less than a hydrogen atom, but for such a big one, it's really a bit small. And 4 times 10 to the minus 12 meter, which is bigger than an atomic nucleus, but is small compared to an atom. And inside the ball, there is of the order of 20,000 carbon atoms, presumably. So carbon nuclei under very high pressure, because there's supposed to be a skin of this radius capital R, which is approximately equal to R with the index cloud 3,3 MeV. and this is under high pressure and high PF of the order of 3,3 MeV. And then I should tell that our model is in principle only using the standard model. And I think that is an advantage because, because most models, one would say, for dark matter are presuming a lot of new physics, but here not. And the only thing that is a bit new is that we have adjusted the parameters in a way which we do not perhaps understand yet, so that there are several vacua with the same energy density. And then this is one of these vacua are in the central part of the bubble, and outside we just have the usual vacuum. And then I think I should, so to speak, boost a bit about some of the numerical order of magnitude only coincidences that we find. And told very optimistic, we say that the dark matter is, as I try to put a few slides in a second, to argue that in literature it is already some people who believe that the dark matter interacts with itself, and that for low velocity, this interaction is so that this very important parameter which can be sigma, the cross section for scattering, or you have one heavier particle with a bigger cross section. So you basically can only study phenomenologically the sigma over m, and therefore sigma over m occurs again and again in our formulas. And now at very low velocity, the value 150 centimeters square per gram for this quantity sigma over m has been measured, if we are optimistic, and we pretend that if we interpret our estimates and calculations, we somehow could say that we predict it to be 314 centimeter per square. And here are some tables of investment. Yeah. What? Then I think I will just show one of the pictures. Here is showing that the non-interacting, only gravitational is not good. And here is another table of them. And here is probably the nicest table, which shows together several estimates of how the cross-section or mass goes with this. And the dark matter, we are estimating the absolute rate very crudely, and it agrees both for Dame Libre and for the very new, rather new xenon 1 ton mysterious extra events of electron type. And we also have looked at that they are coming this 3.55 keV radiation from Tycho Brahe supernova. And but these are good. But what is a little bit bad is that if we have the same effect for the xenon 1 ton and for the Dama, then it is not so nice that they don't agree so well, but only by very crude order of magnitude, even being a couple of order of magnitude different. Because if it is two experiments seeing the same, you would have expected you should see the same. But here is a picture showing what the main thing is, that it should come down. But if the time is out, I should probably stop and tell that we have some calculation. And maybe the most important is that these experiments, both Dharma and the xenon extra events, have the same average energy of the excitations. This, I think, is a very strong indication that is really the same thing one is seeing. And then I think I will simply say thank you and show you at the end the table of our great achievements, but I'm not sure you can see that. But thank you.
Thank you very much, Holger. Are there questions from the audience?
Yeah.
From the internet?
Yeah, hello. Can you hear me?
Yeah, please, Alexander.
Yeah, finally I fixed my microphone. Unfortunately, it was not done for my talk well. But anyway, Holger, what's the mass of your Pearl model, dark matter from your Pearl model? What's the typical mass range?
And the mass we are saying is about 100,000 or 20,000 atomic units, which means there's about 100,000 or 20,000 nucleons in it, and this and this is what is matching. I mean, we use that to need the radius of the little pearl inside, because we think that from other fitting we know the density there, and then we can fit this, and we can see that it matches with this cross section or mass of 150 centimeter, but it is 100,000 GeV, so to speak.
I see, but what's the binding energy? And at which temperatures of the universe evolution this dark matter is formed? So that's my
we have not done it very carefully for this one, but we did, and I think it will be about the same. We did it for a previous version of the model, where these dark matter pearls were very, very big. And then we had sort of barely, but we managed that the estimates of when it should be formed would manage to be just barely before the nuclear, the Big Bang nuclear synthesis.
That's my worry. Actually, my exactly question about, I'm driving to this because my worry that it can inject the additional degrees of freedom for BBN and nucleosynthesis, well, for BBN, and it can spoil BBN potentially. That's what.
Yeah, that's exactly why we were so nervous that it should be finished just before. And I think it is mainly depending on parameter that is not so changed, since our big pearls relative to small. So I think that it will probably still be so that just barely at 1/100th of a second or so, these pearls are essentially finished, and and they are there. So, but that's at least what it should be, because I think it would be not good to put it later, because then they would seriously disturb it. Because you see, now they contain nuclei in large amounts, 100,000 or 20,000 in each, as we said. And if you form them at a later point than Big Bang nuclear synthesis, the amount of nuclei would be completely too many, because we know there are 6 times as many dark matter. So they have basically to be finished before we before the Big Bang nuclear synthesis. But I think this is also
yeah, that's important. Yeah, thank you. Yeah.
Thank you very much, Holger. So we can move to the next speaker.
yes.
Is Marco Cirelli, who's going to talk about sub-GeV dark matter and X-rays. Marco, can you hear us?
Yes, can you hear me?
Can you speak?
Yeah, I'm talking.
I cannot hear me.
I
am talking. Yes, I'm talking. Can people on Zoom hear me?
Okay.
Yeah, we can hear your voice a bit lower, but it's fine.
Okay, then I will share my screen and I'll try to speak loud. So hopefully you can see my slides now.
Yes.
Okay, shall I start?
Minutes.
Okay, thanks. So thank you very much for giving me the opportunity to talk here. I'm sorry I couldn't be in Corfu, but as organizers know, someone in my family passed away last summer, so I had to change my plans. Anyway, I'm going to talk about dark matter as well, and I'm going to talk in particular about the sub-GeV dark matter, where with that, essentially, I mean something which is in the mass range of 1 MeV to 10 GeV or so, 5 to 10 GeV or so. But before I get to that, my sort of introduction would be that we have been obsessed when we talk about dark matter candidates in the past 50 years or so with the weak scale, so the mass scale around 1 TeV. And that's where the thermal particles are produced in the universe, so where you produce dark matter in a thermal way. But of course, the mass range of possibilities for dark matter particles is much, much larger. And actually, we have seen already an example of this plot in not earlier than 2 talks ago, 2 or 3 talks ago. So you can go to a mass of very light particles of the order of 10 to the minus something EV, and you can go as large as solar masses or so in the case of primordial black holes. This covers, as you know, 90 orders of magnitudes. And we have been obsessed by this thermal scale, about 1 TeV, but of course, we should explore all the rest of the parameter space. So as you all know, this point in the parameter space, this range of the parameter space is where we talk about WIMPs, so weakly interacting mass particles. And let me go for a couple of minutes into WIMPs to tell you, as you know very well, what are the good characteristics of that. Well, to me, WIMPs are well motivated as a dark matter candidate for 2 reasons, for 2 pillars, which, let's say, which are completely independent from each other. The first one is that we are expecting, or we were expecting, maybe to have a new physics at the TeV scale because of other problems, such as the hierarchy problem and so on, the mass of the Higgs and so on. And the second pillar, which is completely independent from the first one, if you think in detail, is indeed the thermal freeze out. So the fact that these particles can be produced automatically in the right abundance if we throw them in the thermal bath of the early universe. The other reason why the WIMPs have been so popular in the past few decades is that they can be tested in the 3 standard ways, which are direct detection, indirect detection, and collider searches. And many experiments have been designed in these 3 different strategies to test them. In part because indeed WIMPs were popular, but also in part because we have the opportunities and we have the technology to test this kind of candidates. So the thermal freeze out mechanism is very well known. It essentially in one slide, it consists in noticing, in paying attention to the fact that if you take the evolution of a particle that I call chi during the history of the universe, in order to get you get the final abundance omega chi or omega x, which is represented here, and in order to get the relic abundance that you observe in the universe, about 25% of dark matter, you need to have a particle which has an annihilation cross-section of the Fermat's number 3 to the minus 26 centimeter cube per second. And this number, this annihilation cross-section, is given naturally in the case of weakly interacting massive particles by the ratio of the coupling square divided by the typical mass of the particle, which is 1 TeV, typical of the weak interactions. So this magic number gives us what we precisely need in terms of dark matter in the universe. Okay, so that's why I was saying that this mechanism has been so popular and these candidates have been so popular in the past few decades, and so many experiments have been designed and performed in the different realms to be able to test them. Now, what I want to argue is that we should probably pay attention also to other ranges of parameter space, and the one in which I'm going to pay attention today is the one slightly below the GeV scale, which is so-called sub-GeV dark matter. Where with sub-GeV, as I said, I intend something between, say, 10 MeV up to a few GeV or so. And the question I want to ask myself, so the guideline of the talk will be, can I have some sort of sub-GeV motivation like I have those for the WIMP particles? So can I be able to produce them in a sort of natural way? Are there theory models that motivate them in a similar way as to the WIMPs? And even more importantly, can I test them so efficiently as we have been doing in the case of the WIMP regime? So let me first start with a brief discussion of what the theory models are for sub-GeV dark matter particles, including the production mechanism, and then go to a little bit of detection, and in particular, indirect detection, which would be my focus. So there are several models actually which predict or at least imply the existence of dark matter at the sub-GeV scale. And let me go through some of them briefly. The first one, not in chronological order, but just as a matter of principles, if you want, is a very simple idea, which is anyway rather powerful. And it's called the WIMP-less dark matter paradigm, which is also in some sense connected to hidden sector dark matter, or call it also secluded dark matter. So the idea is indeed very simple, and it's the following. As we saw before, in order to produce the particle thermally in the right abundance, for WIMPs, we needed the annihilation cross-section, which was of the order of alpha weak square divided, the quick coupling divided by the mass of the weak interactions, typically TeV square. Now, the basic observation, which goes back essentially to this paper here, is that you can obtain the same magic number of the annihilation cross-section if you have another kind of interaction, a new dark force, which I denote with X, which has a coupling of the order of alpha X, which points naturally to another mass, which I call now here small m, which replaces the typical mass of the weak interactions. So if the coupling of this new force, Gx, say the coupling which goes into the alpha constant here, is naturally smaller than the weak interactions, then you have also that the mass will be naturally smaller. So the mass predicted for the mass of the dark matter particles will be also smaller, of the order of, say, 1 GeV or 100 MeV or something like this. And the production mechanism for this particle will be indeed the thermal one, just with these new interactions mediated, for instance, by a boson phi vector, say, or a boson phi, which freezes out exactly in the same way as the weak interactions did before, and then the phi will mix possibly with the standard model particles such as the gamma, the photon, and the Z, and then decay into standard model fermions, for instance, in this example. So that's a very simple idea, which points to the possibility of having a smaller mass of dark matter particles. Nothing points precisely to a precise value. It doesn't have to be necessarily smaller than 1 TeV, can be also larger than 1 TeV, but still this opens a new possibility in some sense. Another class of models is the so-called SIMP model, so strongly interacting massive particles, for which something called the SIMP miracle holds, in the words of the paper which is listed here. So here we have a scalar dark matter, which of which the relic abundance is set by these 3 to 2 processes. So 3 dark matter particles annihilate with a coupling alpha effective here into two dark matter particles. This is similar to the so-called cannibal dark matter models, but a bit different for some specifications. And if you do the same computation as before, as we did for the WIMP case, so you follow the Boltzmann equation of the density of this dark matter particle through the history of the universe, you find out that differently from before, now the mass of dark matter particle is sort of individuated by a combination of constants, which is not the same as we had in the case of WIMP. And if you plug in, actually the powers are particularly different because of these 3-to-2 processes. And if you plug in the numbers, you realize that this process points naturally to 100 MeV in mass. So you see that in some sense, in this system, in this setup, there is a natural scale, which is like the QCD-like of 100 MeV or so, which comes out assuming that the coupling is sufficiently large, of the order of 1, for instance, even 4 pi or so. So there is a sort of dark QCD that comes out in some sense naturally from this kind of setups, in which you have a typical scale of 100 MeV for the dark matter particle and a typical large coupling for this new force, which is why we call it a strongly interacting massive particle. So yet another model that points to 100 MeV dark matter particle. And then there are more phenomenological models, more phenomenological ideas. For instance, the old idea that goes back to Céline Boehm and Pierre Fayet back at the beginning of this century, in which they proposed that the famous 511 keV excess seen at the galactic center could be due to the annihilation of very light dark matter scalar particles, so with a mass of the order of 1 MeV. And so this is more phenomenological. It's just a new way to introducing a mass of dark matter smaller than 1 GeV, which at the time was really not really popular, due to responding to a phenomenological observation, which is the 500 keV excess. And more generally, in the recent years, for instance, in this summary paper by Katrin Zurek and collaborators, people have started investigating the so-called simplified models for the case of light dark matter particles. Simplified models means that essentially you don't build the whole theory, but you just assume the basic ingredients. So you have scalar dark matter, which can annihilate, which can interact with the hadrophilic scalar mediator. For instance, this is one of the cases that you can consider. So through this simple Feynman diagram here, for instance, into top bar, because it's hadrophilic, and so it goes into quarks. And this is the simple Lagrangian that you have, and you can do the phenomenology of it, for instance, constraining the mass of the mediator, M5, and constraining the mass of dark matter of the order of, as you see, a fraction of MeV or of an MeV to about 1 GeV. And you have several experiments that can play their role here. You can do the same for other kinds of simplified models. For instance, consider scalar dark matter a leptophilic scalar mediator. So leptophilic now, it couples to leptons, and you can do the same kind of phenomenology. Or you can consider fermionic dark matter coupled to a vector mediator, for instance, dark photon, and we go back essentially to the models we discussed before. And you can do also the phenomenology of these, again, pointing towards this range of masses of the order of, say, fraction of an MeV up to some GeV or so. So this is by no means complete, but I would say that there are theory models that point to sub-GeV dark matter. I have listed some of them here. So the Wimpless idea, the SIMP miracle, the more phenomenological models such as MeV scalar dark matter, and the simplified models I just discussed, plus something which I didn't enter, which is asymmetric dark matter, which points to a mass of the order of 5 GeV or so in its more simplest realization. So my summary, let's say, from the theory side is that there are indeed some theory models that motivate sub-GeV dark matter. They are interesting. It's true that they don't point to any specific miraculous achievement like the WIMP paradigm did, but my takeaway message is why not, in some sense. And I don't mean this to be discriminatory, let's say, towards a sub-GeV dark matter. I mean that we should keep an open mind and do not leave any stone unturned. And so, in particular, also look at sub-GeV dark matter, the case of sub-GeV dark matter. So that's it for my theoretical and say production mechanism motivation. And now the question becomes, how can we test these particles with a mass of below a GeV? So the first idea is direct detection. But the problem with direct detection is that the basic observation is that if the particle is so light, so less than 1 GeV, then the energy which is deposited in the standard strategy of kicking a nucleus in an experiment such as indeed the DAMA or xenon or other is too small. So just for kinematical reasons, if the dark matter particle is light, the energy deposited will be below threshold for a typical nuclear recoil experiment, and so you will see no signal in experiments such as xenon, LUX, and the others. So the idea is to move to something else, some other strategies, in particular looking for electron recoil signals, or looking for the so-called Migdal effect, or even open new experimental strategies of which in the past few years there has been no luck. So this is a short list of ideas for how to direct detect sub-GeV dark matter particles, and you see that you can go from many different ideas like Dirac materials, semiconductors, or diamonds, color centers, all sorts of different crazy or less crazy ideas which are being developed in the past few years and right now. So that's for direct detection. The other possibility is to try to detect them at colliders. And here, if you want, the problem is that the characteristic is that again the missing DT signature for this kind of dark matter would be below threshold for the LHC experiments. We are talking indeed about a few hundreds of MeV or at most a GeV. So you have to change strategy, and this is what people are doing in many different contexts, and use fixed target experiments or big dump experiments, typically looking for associated states, so particles which belong to the same dark sector in which a dark matter particle is. So typically you fire a beam on a target, and you will see dark matter flying away from one side. Actually, you will not see, but you will see the associated states decaying into some standard model particles, such as a pair of electrons or positrons. So that's also something which is being done. But I want to focus instead to the last possibility, which is indirect detection. And in particular, I want to address the possibility of testing these particles with charged particles, charge mediators, or photons.
You have 8 more minutes.
Okay, fine. So let me first talk about charged particles, meaning that we want to see if dark matter particles annihilating in the galaxy or in other environments, but let's stick to the galaxy for the moment, can produce electrons or positrons or protons and antiprotons if they are a bit larger than the mass of the proton and antiproton, so a few GeV or so. So the idea is that I will look at the signals of annihilation of dark matter particles in the galaxy. So let's say protons, antiprotons, electrons, and positrons. These particles will propagate in the galaxy subject to the magnetic field, to the stellar winds, and to possible shocks in the galactic plane. And then they will reach the location of the solar system where we will detect them in some way. Now, the problem with charged particles is that we are talking about sub-GeV charged cosmic rays. So the typical mass is sub-GeV, and so the typical energy of the electrons and positrons coming in will be sub-GeV. And these particles will not be able to penetrate the heliosphere, simply because the solar magnetic field and the solar wind is screening us from these particles of low energy coming from the galaxy. So our experiments cannot collect, our experiments on orbit cannot collect these particles, and we have no signal to test them. Except there is one exception, which is the Voyager probe, which, as you know, was launched in the late 70s, and 2 of them, Voyager 1 and Voyager 2, and it's still flying outside of the solar system. It crossed the boundary of the solar system, and it's flying outside of the solar system since 2012 and 2014. So Voyager actually can collect electrons and positrons from this kind of models. And this has been used indeed to impose constraints in this nice paper here by Mathieu Boudou and collaborators a few years ago. So the idea is that you have a model of dark matter. Look at the blue lines. propagation B, which is the most likely one. You have a model of dark matter with a mass of 10 MeV, say, annihilating into electrons and positrons. You will have this kind of spectrum, the blue point, the blue, say, edge here, and you can test it with Voyager data, which are these 4 red points that we can see around an energy of a fraction of an MeV. A GeV, it's 100 MeV or so, 10 to 100 MeV or so. And you can therefore impose constraints. Look at the right plot here, the red curve, which is precisely the constraints that you obtain if you impose that the Voyager data are not exceeded by the flux of electrons and positrons coming from dark matter annihilation. So you see that these constraints are very powerful. They go well below the typical annihilation cross-section in cosmology, 3 × 10⁻26, about a couple of orders of magnitude below, down to here. Now, the last part of my presentation is about photons, which is where we did some work recently. So photons are coming from the annihilation of dark matter particles with this little mass. Here we hit a problem, which is the following. If you look at the current experiments, the summary of the current experiments detecting photons in these mass ranges, you see that there is something called the MEV gap. So there are current and past very well performing experiments in the high mass regime. So Fermi, for instance, about 1 GeV and up, 100 MeV and up. And there are high performing experiments also in the low part of the mass of the spectrum. For instance, integral, which is down here, the black line, or these other ones here. But there is a sort of gap around an MEV, say between a fraction of an MEV and 100 MEV, where the sensitivity of the current experiments is not very good. And the most important one is COMTEL, which flew in the 90s and which is still being used here. So there is a sort of gap to fill here in some way. And if we are interested in sub-GeV dark matter particles, this is precisely where our signal will fall. So indeed, there are some groups which have obtained some constraints using precisely this data that I mentioned from COMTEL and also some others. So for instance, in this paper here by Essig a few years ago, you see that they can obtain some bounds, typically with this shape here, the order 10 to the minus 28 for a mass of 1 MeV, up to 10 to the minus 24 for masses of 10 GeV. But still, this is not particularly competitive. So our basic idea was the following: how can we sort of go around this gap and try to fill and derive meaningful constraints in this kind of regime? Well, the idea is to use the inverse Compton scattering effect and use the X-rays experiments such as integral or the other ones which are down here. So let me illustrate in the last 4 minutes the idea. The idea is the following. So consider a dark matter with a mass of a sub-GeV, say, to fix the idea, say, let's say 1 GeV or so, that annihilates into these 3 annihilation channels, electron, muons, and pions, which are the only ones which are open for such a small mass of the dark matter particles. And let's focus, for instance, on the Milky Way, so our own galaxy, assuming a standard profile for the dark matter distribution. So the data that you have at disposal are indeed those of integral here, and those around, say, a fraction of an MeV, and those of Fermi, which start meaningfully at about 100 MeV or so. So you see that we have this gap of which I was talking about before. So the dark matter that I just showed will annihilate, for instance, in the case of annihilation into mu plus and mu minus, and this will make a final state radiation, so emitting a photon that I can hope to detect as a final state radiation indeed down here. So this is the spectrum that you get from a mass of dark matter particle of 150 MeV. And as you see, you fall below the sensitivity of Fermi. We are too much to the left to be sensitive by Fermi. We can also consider the radiative muon decay. So these muons will decay into the usual way, also emitting a photon, a soft photon in some cases. And you might think that this is irrelevant from as far as we as particle physicists are concerned, but actually when the muons are almost at rest, this will be important. And so we'll give you a contribution which is important, and it's depicted here by the RAD spectrum, which is still too short in terms of energy with respect to the Fermi data. So the basic idea is to use the inverse Compton scattering, which means the following. So the electrons and positrons, which are produced by the decay of this, by the annihilations and then decay of these charged particles, so electrons and positrons in the galaxy, will hit a CMB photon or a starlight photon, so the ambient light in the galaxy, and they will be upscattered, these photons will be upscattered to larger energies because they absorb the energy of the electrons and the positrons. This is the so-called inverse Compton scattering, which is inevitably associated whenever you have some charge states, such as electrons and positrons, which come out in the annihilation chain in all these cases here. And these give you this kind of spectrum, so a very important bump, a very important contribution in the low part of the energy. And here, the punchline of my presentation is that the total spectrum will come and touch the data from X-ray experiments, which in principle were not a concern for you if you had looked only at final state radiation or radiative decay, because this many orders of magnitude is gained thanks to inverse Compton scattering. So inverse Compton scattering allows us to probe sub-GeV dark matter with data from X-rays, which are even much lower in energy. So we did an analysis using integral SPI data. So the first one we did, and then we are updating this with more recent experiments. I'm not going to discuss this. We just take the galaxy, we chop it into pieces, and we look at this data from integral that we have just reprocessed. And what we get in the end, the final results are these. So this is the same plot we saw before with the mass of the dark matter particles, say 1 MeV to a few GeV. And this is the annihilation cross-section. These are the bounds that we get for the different channels. See, electrons, muons, and pions. The bounds that I showed before are those from ESIG, which are a bit more powerful than ours here, but less powerful than ours here. Those from Voyager, same story. They are powerful here, but not here. And then there are bounds from the CMB, which I don't have the time to discuss now, but they are stronger in case they are S waves, but much weaker in case that the annihilation of the CMB is P wave. So in some sense, our bounds, which do not depend on S wave or P wave, are more solid and they cover this range of masses. So my conclusion is essentially the following, that sub-GeV dark matter is an interesting regime and we should look at it. Why not? It's a very emerging field in some sense. The indirect detection for this kind of models is much more challenging than WIMPs for the reasons I discussed. Direct detection and also in the colliders. And the idea that we had is that if you use inverse Compton scattering, you can test it using X-ray data and therefore impose the stringent constraints that I have just presented here. Okay, I'm finished. Thank you.
Thank you very much. Other questions from the audience?
I see one on Zoom. I don't know if there is.
Yes, there is a question, please.
Thank you, Mark. That was interesting. I'm just trying to understand the separation between WIMPs and your dark matter particles. For me, well, they're still thermal, right? And therefore, you can.
Yes, they're still thermal. Yes, I agree. So if you want, let me try to answer, and then you tell me if you have finished the question, because there is a bit of an echo. So yes, they're still thermal. The basic difference is that, at least to me, is that so in this sense, these particles are based on only one of the two pillars on which WIMPs are based, the one of the thermal production, rather than also the expectation of new physics at a specific scale. Call it supersymmetry, call it X dimensions, call it whatever, but that expectation that we had for many decades. And the other thing is that in this case, we have observed the weak interactions. So WIMPs are motivated because weak interactions exist, while here we don't know whether a force that motivates this thermal production exists or not. That's philosophically the basic difference, you see.
I see. Thank you. I just wanted to make sure that, well, for me, it's still kind of WIMPs in the sense that they're thermal and they are still not extremely light. But what I wanted to ask you, since they're thermal, you need to be very careful about the mass range. well, it's similar comment on the Holger's talk. So I think if it's lighter than few MeV, then it's excluded by Big Bang nuclear synthesis. But you're still sensitive to the range above 10 MeV.
Yes, so there are constraints on that, but unless I forgot something, they are not. They don't impact this. Yeah. Probably at below an MeV, around an MeV, we should pay attention to those. Yes.
Yeah. Below few MeV, I mean, you inject 1 degree of freedom. Right. Or few or more. I mean, and then it's excluded. But it's okay. You still have sensitivity above. What I wanted to tell last thing I wanted to say that the CMB constraint, which I believe that indirect detection at the CMB time. Well, they are very sensitive. So when you say P wave, which are not sensitive, so you're telling that some models where for which only P wave is important, your constraints are really relevant. There's a huge echo.
Yeah, me too. I have an echo. So yes, so the basic point is that if the annihilation is S wave, then the CMB constraint, so essentially independent on the velocity, right, of the dark matter particles, then the CMB constraints kill us completely because they are much more relevant. Indeed, as you say, dark matter annihilates at the time of the CMB, injects energy there, and this is excluded by the observations of the CMB. If, however, the model is such that the S wave annihilation is 0, the S wave component is 0, and the dark matter annihilates in P wave, so with the velocity dependence, then the velocity at the time of the CMB was much smaller, and so the constraints become much less sensitive.
It would be good to have the list of such models to explore further. I mean, P waves like a CMB signal model, because
you're right. So this is completely model independent. We didn't go into this model is S wave and this one is P wave, but it would be interesting to do that to see who survives and who does not. Yeah, thanks.
Okay, there is another question. Yeah.
You may be already partially answered to my question, but still, is there a way to probe P sub GV dark matter with CMB distortions like mu and true distortions? Like, can you hear?
Yes, I can hear. I understood with CMB distortions and then
CMB distortions like mu distortions and true distortions.
You mean the spectrum of the black body spectrum, distortion of the black body spectrum?
Black body spectrum.
Okay,
exactly.
so those, it's a good question. I'm not completely sure. So these bounds that I mentioned here, CMB, these are due to the distortion, the modifications on the anisotropies, right? So this is not what you're mentioning. Looking at the distortions on the black body spectrum itself, I'm not completely sure, honestly. I should have to check. I have the impression that they are not powerful, or at least nobody has looked into those in details, because we looked through the literature and they are not mentioned. But I'm not completely sure, honestly.
There is one more question here.
Don't you consider the indirect?
You can say your name first so that he knows who is. No. Yeah.
In the case of this, don't you consider the indirect channel to neutrinos for the sub-JV?
To neutrinos?
Yeah.
Yes, you can. But in this case, yes, absolutely. But in this case, let's say you get sub-MeV, sub-GeV neutrinos. We didn't look into that, so it doesn't apply to our analysis because we don't get any charged particles in the end, and so we don't get any signal from inverse Compton scattering. You can, I would think that the background from solar neutrinos and low energy atmospheric neutrinos would kill you, but again, I haven't looked into this in detail.
Okay, I think that's all. Thank you, Marco, again.
Thank you.
And all the tickets to the session. Session is over.